Colligative properties, freezing point depression, and molar mass. Calculations. In this video, we will discuss the calculations for the freezing point depression experiment. The goal is to determine the molar mass of an unknown solid using the freezing point depression of cyclohexane. The data shown in this video are data collected by me for this experiment. Recall that this experiment had two stages. First, the freezing point of 10.0 milliliters of pure cyclohexane was determined. Next, a known mass of a solid unknown was weighed out and dissolved in the cyclohexane. For this particular calculation, the mass of unknown that I used was 0.328 grams. Next, the freezing point of the solution was then measured, and the freezing point depression calculated. From the freezing point depression, we are able to calculate the mole concentration of the unknown solution, and then the number of moles of unknown in solution. Lastly, we can use the mass and moles of unknown to find the molar mass. The first step is to plot the cooling curves for your data. Please pay special attention to these next few slides to ensure that you perform this correctly. Plot both of the pure cyclohexane runs on one graph and both of the unknown runs on a second graph. Then, for each run, use at least the final 5 points to calculate the freezing point. You may use more than 5 points at the end, but a minimum of 5 is required. This is done by averaging the last 5 or more temperatures for each of the 4 runs. We will see my two plots in a moment, but first let's calculate the freezing point for the first cyclohexane run. For my data, the last 5 temperatures were 6.8, 6.8, 6.7, 6.7, and 6.7 degrees Celsius. The average temperature is calculated by adding these 5 temperatures up and dividing by 5, which gives 33.7 degrees Celsius in the numerator divided by 5 in the denominator, or 6.74 degrees Celsius. This was repeated for the other 3 runs. For the second cyclohexane run, the average final temperature was determined to be 6.64 degrees Celsius. For the unknown solution, the two averages were found to be 0.84 and 0.42 degrees Celsius. Here we see my plots for pure cyclohexane. First, notice that for run 1, the initial 5 or so temperatures did not fall on the graph paper. They were too high to record. This is acceptable as long as you continue and pick up where the first data point actually falls on the graph. Notice that at the plateau for each run, I have used a ruler to draw a horizontal line indicating the average freezing point for each of the 2 runs. 6.7 degrees Celsius for the first run and 6.6 degrees Celsius for the second run. Next, we see the plot for the unknown solution. Again, there are 2 different runs plotted on the same graph. In this case, all of the data points fit on the graph and are plotted. As before, you will use a ruler to draw a horizontal line at the plateau, indicating your average freezing point for each of the 2 runs. We are now ready to calculate the freezing point depression. In order to do this, we need the freezing points for both the pure cyclohexane and the unknown solution. These values are found as the average of the 2 average final temperatures from each plot, those that were indicated by the horizontal lines. For the pure cyclohexane, we can find the freezing point for the pure solvent to be 6.74 degrees Celsius from run 1, plus 6.64 degrees Celsius from run 2 divided by 2, or 13.38 degrees Celsius divided by 2, which gives 6.69 degrees Celsius. In the same manner, we find that the freezing point for the solution is 0.63 degrees Celsius. Now we can calculate the freezing point depression, or delta TF, which is defined to be the difference between the freezing point of the solution and the freezing point of the pure solvent. For my data, this becomes delta T sub F is equal to the freezing point of the solution minus the freezing point of the solvent, which is 0.63 degrees Celsius minus 6.69 degrees Celsius, for a freezing point depression of negative 6.06 degrees Celsius. As the freezing point depression is directly proportional to the molar concentration of the solute, we can use this to calculate for the concentration. We know that delta TF is equal to negative I times KF times M. Here, M is the molar concentration that we wish to solve for. Recall that for cyclohexane, I is equal to 1 because it is a non-electrolyte, and the value of Kf from the table is 20.4 degrees Celsius per molal. We can rearrange the equation to solve for concentration, giving M is equal to delta TF divided by negative I times Kf, or for my data, negative 6.06 degrees Celsius for the freezing point depression, divided by negative 1 times 20.4 degrees Celsius per molal, which gives a molal concentration of 0.297. We can now determine the moles of unknown that are dissolved in solution. For this, we need the molality of the solution, which we just calculated to be 0.297 molal, and the kilograms of cyclohexane. The mass of cyclohexane is found using the volume of cyclohexane in the test tube, which was 10.0 milliliters, and the density of cyclohexane, which is 0.7726 grams per milliliter. The mass of cyclohexane is equal to the volume of cyclohexane times the density, with the proper conversion factor at the end. This is equal to 10.0 milliliters times 0.7726 grams per milliliter times the conversion of 1 kilogram per 1,000 gram, which results in a mass of 0.00773 kilograms. We can now calculate the moles of unknown that were dissolved in solution. This is just the product of the molal concentration and the mass of cyclohexane in kilograms, or 0.297 moles per kilogram times 0.00773 kilograms, giving a value of 2.30 times 10 to the negative third moles. We are now in a position to finish our calculation and determine the molar mass of the unknown solid. Recall that this is just the ratio of the mass of the unknown weighed out to the number of moles of dissolved unknown, as we just calculated. Or the molar mass is equal to the mass of the unknown divided by moles of unknown, which is equal to 0.328 grams of unknown divided by 2.30 times 10 to the negative third moles of unknown, giving a molar mass of 143 grams per mole. Lastly, as with the previous experiment, you will be presented with a list of potential candidates for the unknown that you dissolved. You will select the compound with the molar mass that is closest to your determined value, and then calculate the percent error in your results. In my case, the data closest matched a compound with a molar mass of 140.56 grams per mole, and I will use this to calculate the percent error. Recall that the percent error can be found as the difference between the measured value and the true value divided by the true value, all times 100%. Or in this case, 143 grams per mole, as I determined, minus 140.56 grams per mole, all divided by 140.56 grams per mole times 100%, giving 2.44 grams per mole divided by 140.56 grams per mole times 100%, or 1.7%. This concludes the calculations for the freezing point depression experiment. As before, report guidelines and a data sheet will be provided on Canvas for you to complete this experiment. Please be sure to contact me if you have any questions regarding this report.